My name is Paul Edison-Lahm. I'm a communications director for the Geological Society of the Oregon Country. I'm the public member for the Oregon State Board of Geologists Examiners and secretary for the Portland NAACP Environmental Justice Committee. This is an amateur's guide to Reed College and Eastside Portland geology. We're going to just start way at the beginning with the breakup of Paideia. The giant supercontinent that housed the dinosaurs started breaking up 280 million years ago. And the consequence has been that the North American continent has been pushing to the west ever since. Well, why is that important to those of us who are here in the Reed College neighborhood? If you remember really old Reed, it was just all ocean. It was just ichthyosaurs and plesiosaurs and other small dying creatures. And so the question for today is, where did all this stuff come from? All these rocks and mountains and ground and soil. It is an amateur's guide, I emphasize, because I'm really concerned with how all of us go into nature and we go with sort of a map in our head, our cultural background, our religion or lack of religion, our scientific view. And then there are these transcendent moments where we pick up a rock or we hear bird song, or maybe there's some instrumentation like a telescope or a microscope, and you make these connections. And those are especially rich in the context of community, whether it's the Reed community or a community like the Geological Society or other groups that we belong to. So that's really the heart of my focus, although I am going to be talking a little bit about geoscience careers and some of the issues that arise now, especially those that concern environmental justice and climate change. So here is the master narrative that most of us who know about geology in the Pacific Northwest, this is the picture that we carry around in our head. It's the story of subduction. And you see that big orange arrow off to the right. Well, that's the North American continent pushing. And as it does so, the oceanic crust, which is the little arrows that are moving underneath, is like a conveyor belt that moves under the continent. The problem with master narratives is that they can get kind of stale, and they can limit our imagination, and they can limit our interest in the complexity that might underlie. The other problem is that many of these master narratives, for a lot of us who have affection for science, imply exploration and discovery. And for others, they may seem more sinister, especially to the extent to which geology in particular, but geosciences in general, have been involved with resource extraction and exploitation of the environment. Moreover, geoscience, geology in particular, has a whiteness problem, a lack of diversity that is more severe than most of the other STEM fields. I think math is the only one that's worse. Even astronomy is doing a better job of recruiting BIPOC and women and LGBT into the ranks of younger professionals and younger scientists. So this is something that geology has started to really take a hard look at, especially since jobs in energy extraction are on the decline. But I want to start with a more humble setting, and that is the Reed Canyon, where we can have these experiences of encountering nature. The great thing about geology is that all you need really are a pair of eyes or hands to pick up a rock. It might help if you have a 10-power magnifying glass. That's not absolutely necessary. It might help if, like me, you have a reckless disregard for personal fashion, but you don't even have to be someone who wants to go out into nature. A lot of this work now can be done behind a computer, mapping, looking at images, and so forth. Where did the stuff come from? Well, the overall story is some of it came from the east, some of it came from the west, and some of it came up from below. Oregon has fantastic geology. This is out in eastern Oregon in Blue Basin. It's the remnant of a super caldera out there. And it's full of fossils, full of mammalian fossils that are of historic importance. Beautiful stuff. This is the Blue Basin on one of our recent Geological Society field trips. The problem in Western Oregon is that it's covered with development, with trees, with grass, and it covers up all the wonderful geology. But we're fortunate here at Reed College in that we have a trench basically in the middle of the college. We have the Reed College Canyon, which allows us to get down to the actual geology. So returning to that scene of in the canyon, the first part of our story is stuff that came from the west. And this is the story of accretion, in particular the Siletzia and Waverly basalts. And I'll explain that in a moment. Accretion is what happens when there's stuff on that oceanic conveyor belt, whether that stuff is sediment, or in some cases, giant island arcs like Japan or in Indonesia that may have formed offshore, but through the processes of plate tectonics, through the process of subduction, get smashed up onto and underneath the existing continent. So that has happened on the west coast of North America multiple times over the past some hundreds of millions of years. In fact, it's how the entire west coast of British Columbia and California and Oregon has been assembled. The particular piece that we're interested in is called Silesia, which was an island arc. About 56 million years ago, it erupted out in the ocean, and about 50 million years ago, it docked, as they say. It smashed into the North American continent, as you're seeing there. So here at Reed College, if we dug down to the basement level, eventually we would find, volcanics. We would find Hawaiian-style basalt volcanics down there that are some 50, 40 million years old. And you can go down to Milwaukee. That's Johnson Creek, into which the Reed Canyon flows, and then Johnson Creek flows down to the larger body of water there, which is the Willamette River. And that's a great place to take a look at some of these really old, we call them Waverly basalts, that are just eroding right out of the hillside there. So these are very old basalts. They're crumbly enough that you can break a lot of them open with your hand. They were sitting in water for a long enough period of time that the silica gets dissolved and carried into any bubbles or vugs that might exist. What you get are cool crystals forming. So these kind of dirty looking, but here it's cleaned up a bit. This is what we call a zeolite, and these are quartz crystals that reformed inside the basalts, and those are just available right along the roadside. You can pick them up there down at 17th and Highway 224 is a really good spot, and also at the confluence of Johnson Creek and the Willamette River. The next piece is subduction, which I've already mentioned. The subduction is responsible for all kinds of wonderful things and catastrophes, from earthquakes to the Cascade volcanoes themselves. So we're going back to this picture. The story is that oceanic crust, because it's heavier and denser than the continent, including the mountains above, that's the story, that it gets forced down, and at about 60 miles down, it starts to release all of that water that was sitting in it for millions of years while it was ocean bottom. The water rises as heat rises. It causes the magma above to melt, and that magma rises as heat rises and erupts as volcanoes. So when we think about the Cascades extending all the way from Canada all the way down to California, we've got Mount Hood, Mount Adams, Mount St. Helens, all the way down past Crater Lake, Mount Shasta, and all the way down to Lassen Peak in California. What you're really seeing there is the point at which the subducting plate reaches that 60-mile or so point, and the volcanoes that are above that point. One really cool fact about rivers and mountains, and here we have where the Columbia River comes from eastern Oregon and crosses the Cascades to flow out to the sea, is that when you have a river that entirely crosses a mountain range, it means that the river was there first before the mountains came up underneath. And the Columbia has been draining whatever the land was to the east of it for tens of millions of years. The Cascades in their current form are only a few million years old in that current position. And so the Columbia has had a chance to cut through the Cascades, creating the Columbia River Gorge. Well, that's as good a place to start our conversation about the geology of the Portland Basin, because the Columbia Gorge and the gap through the Cascades that it creates has been the source of 3 catastrophic floods that have shaped our natural and social history more than anything in the region. One of fire, the Columbia River basalts, about 17, 16 million years ago, that flowed from eastern Oregon and Washington all the way to the sea. One of rock and ice, the Missoula floods, 18,000 to 13,000 years ago or so, that again flowed through that gap in the Cascades created by the river, filling up the entire Portland Basin and Willamette Valley all the way to the ocean. And finally, one of Euro-American settlers in the 1840s and 50s and 60s, who again flooded along the path of the Columbia into the Willamette Valley, displacing the Native American population. So starting with the Columbia River basalts, This is an incredible story. Right here in the Pacific Northwest, the story started about 17, 16 million years ago. These giant fissures, which you see as white lines on the map, opened up in eastern Oregon and Washington, and lava flowed out. Very much the same sort of runny, low silica lava that you see in Hawaii running in rivers from the Kilauea volcano, filling up the entire watershed of the Columbia, following the river through the gap that it creates in the Cascades, all the way to the ocean. So if you've been out to Haystack Rock at Cannon Beach, that is Columbia River basalt that flowed, perhaps over the course of weeks, hundreds of miles to the ocean. Oh, you can see that that's the Silesia and Waverly block underneath. And so our story now has two layers of basement. First, the basalts of the Silesia Waverly, and then next, the basalts of the Columbia River basalt. It might have looked like this if someone had Photoshop 16 million years ago. What it leaves behind, if we were to dig under Reed College, and this is actually a quarry from the west side of Portland, is these mammoth basalts that cool in a fascinating way. And the physics of this is that as the flow cooled, the cracks form perpendicular to the cooling surface. And so you get, in this case, these this is all one flow, several, looks like about 100 feet thick or 70 feet thick. And those cracks are cooling perpendicular to the surface, and they form these hexagonal columns. There's a great example of this actually right outside the Sports Center. This is a beautiful decorative sculptural piece that uses a Columbia River basalt column. So back to the canyon, this humble gray rock, if we were to break it open, we would see as little flecks of feldspar, but it's mostly low silicate minerals like olivine and pyroxene and hornblende. But the geochemistry is fascinating and can tell us exactly which of those flows this belongs to. And that has given us a way of mapping the history of Oregon geology. Next, jumping forward 3 orders of magnitude in time to the Missoula floods during the last ice age. As you're probably aware, the United States was invaded by these huge ice sheets that came down from Canada. Many of those ice sheets blocked the existing river drainages, and in this one case created the glacial Lake Missoula. The ice dam that held that huge lake back broke many dozens of times, perhaps as many as 100 times. And as a consequence, this huge torrent of water came out into eastern Washington, carving out the channeled scablands, rushing past these horrifying JPEG artifacts, following the path of the Columbia River, all the way into the Portland Basin and down into the Willamette Valley, sort of sloshed around there in what we call Lake Allison, a sort of temporary lake, and then it slowly drained out to the sea. Might have looked something like this. These are we call them the boring buttes from Boring, Oregon. So Mount Tabor, Kelly Butte, Powell Butte, and so forth. They would have been covered up to a height of 400 feet by these floods, of which at least 40 made it into the Portland Basin. We know from Calapooya accounts that there were people living in the Willamette Valley who witnessed these floods. And so it's not unreasonable to think that there were people perhaps in sheltering at the top of those buttes, or maybe who made it out of the valley in time. But that's an important part of our history. Dr. David Lewis, a researcher at Native American history at OSU, posits that one reason we haven't found more evidence of this is that we haven't had the curiosity to look. So those floodwaters filled up the Portland Basin to a height, as I said, of 400 feet and slowly drained out. As the waters came out of the gorge at about 60 miles per hour, they slowed, having more space to spread out. And as they slowed, the first thing they did was they dropped the heavier stuff, their loads of boulders and gravel. So what you're seeing there with the darker beige color is that carpet of gravel, that apron of gravel that extends from the Columbia Gorge all the way into southeast Portland. It looks like something like this if you quarry it out and dig down. It's very tough stuff because as the water comes in, it pushes the gravel in successive layers that we call crossbeds. And so you'd find this if you could dig under the grass and trees at Chavez at 39th. You'd find this at the hill. This is why there is a hill. It's very durable because it's all of these cross-bedded gravels. Where the water had a chance to still and flow out gradually, there was more time for the finer sediments to settle. So if we were to cut down into those fine sediments, we would see these. These are called rhythmites. And what you're seeing is a layer of gravel, of light gravel, that fell first out of the water, and then the silt and sand above it. And then above that, with the next flood, another rhythmite that is composed of gravel and then silt and sand. This is how we know that there have been over 40 floods that made it into the Portland Basin and into the Willamette Valley. That's what's under Reed College. Those Missoula flood fine sediments all the way from Chavez 39th down to the rhododendron gardens and the golf course. If we pull back a little bit, we can see that, again, the coarse grain deposits, those heavier cross-bedded gravels, are what's up the hill. And down the hill in the rhododendron gardens, we have Missoula flood channel deposits. And there are two theories about how those got there. One is that this was the backflow channel as the floodwaters flowed out. Another theory, of which I'm quite fond, is that this was actually also an ancestral Willamette River channel. And it has that appearance, but that's something that students might want to look into. So going back to the canyon, the diagnostic rock for stuff that came from out of town are these quartzites, these humble orange rocks that are metamorphosed sandstone. So to get a quartzite, you got to have sand. To get sand, you have to have a mountain that eroded into a stream, then a river, then perhaps a delta, then was covered up, became a sedimentary rock, a sandstone, then under a mountain range, metamorphosed into this beautiful quartzite that has this kind of glassy quality to it if you break it open. That took a long time. And those metamorphic rocks are very old, sometimes billions of years old. And we don't have rocks that are that old in this part of Western Oregon. So they had to come from far away. And in this case, we think that they came from the Montana Fold Belt out in Montana or Idaho, down either the Snake River, which is that yellow band there, or the Columbia River, the purple band. And when you see these rocks, and you'll see them sometimes in sidewalks or stream beds, that's a sign that they came either by river or by flood to the Portland Basin. Looking at the sand itself, we find another flood signature, perhaps. This is what sand normally looks like after it's had a nice gentle bath flowing down a stream or river. But this is what the sand looks like in the Reed Canyon. And this, we think, might be a flood signature, this really heavily fractured feldspars and quartzes. Next, boring volcanics, named after the Oregon town of Boring, are what formed all of those buttes that I pointed out before, Mount Tabor, Mount Scott, and so on. And they are a mystery. We know, for example, what causes the Cascades, or we have that theory of subduction, that again, the magmas come up and where the crust is going down, and we get these pointy volcanoes that we call stratovolcanoes that form the Cascades all the way from Canada down to California. But in front of them, we have all of these low-lying cinder cones and shield volcanoes. And they're actually, many of them are about the same age. Mount Tabor's about 200,000 years old. Mount Scott maybe 2 million years old. Mount Hood in its present form is maybe 1 million years old also. But these boring volcanoes are made of that Hawaiian-type runny basalt, and so they don't form the same sort of stratovolcanoes. Instead, they form cinder cones and low-lying shield volcanoes. And they are a geologic mystery because we don't know why they're coming up where they are. We've had some 60 or so volcanoes in the past 2.6 million years in the Portland metro area. As young, out, say, in Beacon Rock and the Gorges, 58,000 years. So this is a period of volcanism that we are still in. And so we might be able to expect another one of these popping up in the Portland metro area in the next 15,000 or 50,000 years. But I don't want you to worry about that. That's something you don't need to worry about if it's going to be tens of thousands of years before it happens. What I want you to worry about is the Cascadia quake. This was something that was not known to Western science until the 1980s. What happens when that crust is subducting is that it gets stuck and periodically releases, resulting in an earthquake that's magnitude maybe 8 or 9. This was known to the people who lived here. This was known and is recorded in Native American stories of thunderbird and whale, for example, all up and down the Pacific Northwest coast. And there were clues. For example, this drowned forest at the coast. These trees, looking at the tree rings, all died in the same year. They died when, as a result of the earthquake, the ground dropped, the tsunami came in, and the trees died. But the real clue was something called the orphan tsunami. The Japanese have kept very careful records of tsunamis, and usually those tsunamis are connected to earthquakes. But there was one tsunami back in January of 1700 that wasn't connected to any earthquake. And so what scientists have determined is that if you back the timeline up, assuming that a tsunami travels at about 500 miles away from an earthquake, you come out with the date of January 26, 1700 at 9 p.m. for the last Cascadia quake in the Pacific Northwest. Now, I think that 9 p.m. is kind of scientists showing off, but looking at the data for the past 8,000 years or so, it looks like on average, we have a magnitude 8 or magnitude 9 every 300 years. Well, 1700 was 321 years. So for some geoscientists, this suggests that we are, as they put it, 9.5 months pregnant for the next earthquake. I think the actual prediction is that we have a 30% chance in the next 50 years of a magnitude 8 or magnitude 9 Cascadia quake. Well, what does that mean for us here? I'm going to superimpose a hazard map on the map we saw earlier. It means pretty much what you think. The red is bad, orange is a little less bad, and the sort of cream colored is the best place you'd want to be in an earthquake here in the basin. Now, we won't have a magnitude 8 or 9 here in Portland. That'll be what's experienced at the coast, which will then be hit with a tsunami. But we'll have only maybe a magnitude 6 or 7, but it'll go on for 4 or 5 minutes. The worst place to be is down by the river, where in the 19th and early 20th century, they dredged up the river bottom and they filled in the surrounding floodplains to create areas for industrial development. In particular, this is bad in Northwest Portland, where we have what's called the critical energy infrastructure. And in the event of a catastrophic quake, the ground under these tanks will liquefy, the tanks will fail, catch fire, releasing pollutants, ammonia and chlorine into the atmosphere, and float downriver, causing environmental catastrophe. So this is a terrible problem, obviously, and has great environmental justice consequences for populations, communities of color in North and Northeast Portland. And we'll come back to that in a little bit. The less worst place to be is in the orange, which are, if you remember the previous map, those Missoula fine sediments. And Reed is on such an area. Here, you want to be in a building that's secure, that's not made of unreinforced masonry, for example, that's not going to fall down around you, someplace where you can shelter. The best place is to be up on those cross-bedded gravels. Up above 39th Chavez would be a much better place to be in an earthquake. So again, where are we? Well, I'm going to superimpose the geologic map first so you can see the lighter colored fine sediments. And then superimposing the hazard map. That looks bad for Elliott and the old Dornblock in particular. I am told by geoengineers that this is maybe more conservative than it appears, and that the water table is actually about 40 feet down, and so the chances of liquefaction are pretty low. I noticed, though, that Reed is starting to do most of its new construction in the upper quadrant up there in the old soccer field, where the ground is a little more steady. Elliott in particular, it turns out when we looked at the archives, is actually reinforced concrete, despite having a veneer of brick and limestone. And so you're probably safer in the building to shelter than to run out and maybe be injured or killed by falling masonry. This building, however, the Weiss wing of the library, though built in 1964, is actually unreinforced masonry. And so Reed is reconstructing it. I don't know if that's actually started, but fortunately Reed has the money to do it. Where it's a real problem is for communities that don't have the resources, or small businesses that don't have the resources to do these very expensive restorations to bring their buildings up to seismic code. So this takes us to the unreinforced masonry issue that emerged in Portland over the past 3 years. The right way to do this is what California has been doing since the earthquake of 1906, which is prohibit the building of unreinforced masonry buildings and require retrofitting of existing buildings. This has tremendous economic cost, and it's been spread out in California over a century. We only discovered that we had this threat 30 years ago or so. and the codes are about that old. So what the city of Portland did, because it didn't have enough political momentum or agreement to pass an ordinance that would require retrofitting at great economic cost, was to pass this ordinance that required a notice be put up on unreinforced masonry buildings. And all it says is that this building may be unsafe in the event of a major earthquake. It doesn't even say what you should do. So this got a lot of pushback from wealthy property developers and small business owners like folks up in the Woodstock neighborhood, music venues, and most significantly, the Black community, which has a historic stake in the presence of the Black churches in Northeast Portland. In particular, the Portland NAACP, in coalition with property developers, pushed back on the ordinance with protest and through a federal lawsuit managed to get it stayed and eventually reversed. The next step for us is addressing the critical energy infrastructure. This is an issue for all of Oregon because the infrastructure provides 95% of the energy for the entire state, and also the energy that would be required in reconstruction efforts after an earthquake. Obviously, there are major implications as far as climate change and whether we want to reinvest at all in this infrastructure or relocate them. The politics of this, I think, are going to emerge over the next decade. So a couple of interesting horizons in geology that I want to talk about real quickly. One is this whole issue of where the Columbia River basalts come from. Our general theory of the basalts is that there's a hot spot underneath, very much like the hot spot underneath the Hawaiian Islands. And the model for this is that you've got an oceanic plate that's moving past the hot spot. And as it does so, islands pop up from it, and you get really a sort of history of the island chain recorded on top of the oceanic plate. So the islands, if you know Hawaii, you know that the youngest is the island of Hawaii, where you have active volcanism today at Kilauea, and then successively older and older as you go to Maui and Molokai and Oahu and so forth. So similarly, we believe that there's a hot spot that is currently under the Yellowstone caldera, because if you march the timeline back, you see that there are progressively older and older calderas that go back to about 16 million years, and that's when the Columbia River basalt started. So it's believed that there's a connection between that hot spot that has been in the same place as the North American continent has moved west over it, and a connection between that and the Columbia basalts. But the alternate theory of volcanism involves subduction. And as in many areas of science, the advances come to increased instrumentation. And so here's a picture of, this is a more complex picture of that oceanic plate, the Farallon plate, underneath the Western United States. And this picture is coming to us from advances in seismic tomography, where you have a dense network of seismic stations that pick up and interpret the signals from earthquakes and can actually recreate a three-dimensional model of what's underneath. So this in particular comes from the important work of Karin Signalk. And so going back to that original master narrative that I showed you, this is a much more complex version of what's going on down there, and is revolutionizing to a large extent the story of how the Western United States was assembled. If you're interested in this, by the way, Nick Zentner is doing wonderful work on his podcast and video streams. He's a professor of geology up in Ellensburg, and I highly recommend his podcasts and video streams because he's talking about precisely this frontier in geoscience. I want to touch a little bit more on the Portland Basin just for a moment, because there's some mechanics there that are critical to forming this northwest, southeast trending trench that have to do with the fact that the subduction is occurring obliquely. That is, the Pacific plate is sort of coming in at an angle, and it's causing the whole state to rotate. And this is shown by both GPS and paleomagnetism. So those vectors that you're seeing are GPS tracks, and they show that there's sort of a center of rotation in eastern Oregon and northeastern Oregon, and the whole state is turning around, getting jammed up against Canada, which is causing faulting. This is confirmed, incidentally, by the paleomagnetic record, which shows the reversals in the polar reversals that are recorded in the basalts over time, showing that Oregon and Washington are rotating at a breathtaking rate of 1 degree every million years. The local result of this is that you get this kind of pull-apart basin effect, where you get parallel faults that open up, and that's one reason that we have so many northwest, southeast trending highways like Highway 30 and Highway 26 and Highway 224 in Portland, because they follow generally the trends, the tracks of those faults, including the Portland Hills Fault. So I want to touch a little more on the question of Native American history. Again, I would really highly recommend David Lewis's website for history of the Grand Ronde peoples in particular. The story is tragic of the extent to which the tribes were first decimated by disease and malaria in the early part of the 19th century, and then forcibly removed to reservation in the case of Grand Ronde, the peoples of Kalapuyan peoples and Clackamas peoples who lived here in the Portland Basin. Those that had survived the diseases were forcibly removed to the Grand Ronde Reservation on the coast, along with 26 other tribes. In what's called the Oregon Trail of Tears, many marched on foot up the coast. There were other atrocities, especially in southern Oregon with the what were called the Indian Wars of the time. So that history is pretty grim and unfortunate and leaves this tragic gap in the history. But it's important to emphasize that Native American presence in the Pacific Northwest is much more than just that history of colonization. The current Native American population in Multnomah County is estimated to be over 70,000, representing 380 tribes from around the United States, many of whom relocated to the Portland area after the tribal terminations in the 1950s. Portland also has some of the oldest Native American advocacy groups, as well as there are being 9 sovereign tribes in the state of Oregon. So tribes don't want to be thought of as a historical footnote. Rather, they need to be understood as having political influence and cultural import today. So with that caveat, I want to talk about something that we discovered accidentally a few years ago, which is that there was a projectile point found in the headwaters of Crystal Springs Creek. Now, the state keeps a very tight lid on the actual location of these finds, but it turns out that the headwaters of Crystal Springs Creek is the Reed Canyon, probably in construction that happened around 1986. Why this is important, I think, is because it really does bring awareness to the fact that this is land that has been peopled for over 10 millennia. The projectile point was a wind dust point, which would date to about 8,000 to 10,000 years ago. I would love to see Reed, if this is in the interest of the Grand Ronde tribe, and it really needs to be for any action to be taken on this, I would love to see Reed support the effort to learn more about this particular find. I think it would be it's important to the history of the college, and I think it's important to the history of the Portland Basin. So what next? Well, if you're interested in geology, I would highly recommend The Bible of Oregon Geology by our good friend, Dr. Bill Orr and his wife, Elizabeth Orr. Also, Dr. Marley Miller's Roadside Geology of Oregon is a very accessible way to pick up on any road trip. Come to our meetup the 4th Saturday of every month and join our social hour at 11, geology news, Q&A at noon, and then special topics at 1. We have our monthly lectures, second Friday of every month. Those have been at Portland State for about 85 years, and they're currently on Zoom. All the video content for that is on our website, gsoc.org. When we are able, we will once again have our wonderful field trips where, as amateurs, many of us get to stand shoulder to shoulder with professional geologists and listen to them talk about their research. This is Karin Patridge out at Blue Basin again on a recent field trip. I have been doing a downtown building stone geology trip for about a decade now. And so we bring people down with hand lenses to look at the fantastic fossiliferous rocks there at the Hatfield Courthouse or the Pioneer Mall. We also do an East Side bike geo tour that runs from Steel Bridge down to Milwaukee. And we've worked with the Johnson Creek Watershed Council to create a Johnson Creek Watershed Geology Tour. And that includes Reed College because the Reed Crystal Springs is part of that larger watershed. So you can find out more about GSOC at gsoc.org. Thank you very much.